Welcome to the video lecture on the subject Computer Vision, Unit 4 3D Construction, Part 3. I am Dr. K. Padmapriya, Assistant Professor, Department of ECE, Government College of Engineering, Tirunelveli. Point-based representations. Triangle-based surface models assume that the topology and often the rough shape of an object of the 3D model. While it is possible to remesh a model as it is being deformed or fitted, a simpler solution is to dispense with an explicit triangle mesh altogether and to have triangle vertices behave as oriented points or particles or surface elements, which are called as, in short form, as surfels. To endow the resulting particle system with the internal smoothness constraints, pairwise interaction potentials can be defined that approximate the equivalent elastic bending energies that would be obtained using local finite element analysis. Instead of defining the finite element neighborhood for each particle vertex ahead of time, a soft influence function is used to couple the nearby particles. The resulting 3D model can change both the topology and particle density as it evolves and can therefore be used to interpolate the partial 3D data with holes. Discontinuities in both the surface orientation and crease curves can also be modeled. To render the particle system as a continuous surface, local dynamic triangulation heuristics or direct surface elements plotting can be used. Alternative is to first convert the point cloud into an implicit signed distance or inside-outside function using either minimum sign distances to the oriented points or by interpolating a characteristic function using radial basis functions. Even greater precision over the implicit function fitting, including the ability to handle irregular point densities, can be obtained by computing a moving least squares MLS estimate of the signed distance function as shown in the figure. So this is a point-based surface modeling with moving least square MLS method. The first of all, a set of points, that is the black dots, which is turned into an implicit inside-outside function, that is the black curve. So the points over this dots, they are being explained, mentioned here. So a set of oriented points with variable sampling density representing a 3D surface. Here a head model is taken and it is being mentioned here. A local estimate of sampling density which is used in moving least squares, and then it is being reconstructed using continuous 3D surface. Point-based representation. So further improvements can be obtained using local sphere fitting. Faster and more accurate resampling and kernel regression to better tolerate the outliers. A RGBD SLAM system based on a variable resolution circle representation that gets retriangulated as more scans are integrated. Recent approaches to 3D point clouds, they use the deep learning methods. The third one is volumetric representations. A third alternative for modeling the 3D surfaces is to construct the 3D volumetric inside-outside functions. So some of the examples are voxel coloring, space carving, and level set techniques for stereo matching, and using binary silhouette images to reconstruct volumes. Volumetric representations look at continuous implicit inside-outside functions to represent a 3D shape. So first we can see about the implicit surfaces and level sets. While polyhedral and voxel-based representations can represent three-dimensional shapes to an arbitrary precision, they lack some of the intrinsic smoothness properties available with continuous implicit surfaces, which use an indicator function or characteristic function f of x comma y comma z to indicate which 3D points are inside f of x comma y comma z, which is less than 0, or outside, which is denoted by f of x comma y comma z more than 0, the object. So implicit functions are used to model the 3D objects in computer vision where super quadrics are used. To model a wider variety of shapes, super quadrics are usually combined with either rigid or non-rigid deformations. Super quadric models can either be fitted to range data or used directly for stereo matching. A different kind of implicit shape model can be constructed by defining a signed distance function over a regular 3D grid. Using by five kinds of way we can do it. The first kind is using an octree spline to represent this function more closely away from its surface, that is 0 sig. And then it's used to represent distance transforms, then level sets for 2D contour fittings and tracking, and volumetric stereo, range data merging, and point-based modeling. The advantage of representing functions directly on a grid is that it is quick and easy to look up the distant function values for any XYZ location. And it's easy to extract the isosurface using the matching cubes algorithm. Several distance functions are used simultaneously and then combined locally to produce sharp features such as creases. Poisson surface reconstruction uses a closely related volumetric function, namely a smooth 0 bar 1 inside outside function, which can be thought of as a clipped signed distance function. It is either called as characteristic or occupancy function. The gradients for this function are said to lie along oriented surface normals near known surface points and 0 in all other places. The function itself is represented using a quadratic tensor product B-spline over an octree, which provides a compact representation with larger cells away from the surface or in regions of low point density, and also admits the efficient solution of the related Poisson equations. The quadratic penalties used in the Poisson equations are replaced with L1, that is total variation constraints, and still obtain a convex optimization problem which can be solved using either continuous or discrete graph cut techniques. Signed distant functions also play an integral role in level set evolution equations, where the values of distance transforms on the mesh are updated as the surface evolves to fit multi-view stereo photo consistency measures. Deep neural networks have started being applied to the construction and modeling of volumetric object representations. And neural networks construct the 3D surface or volumetric occupancy grid models from single images. So deep SDFs, IM nets, occupancy networks, deep implicit surface, that is DISN networks, and Euclid net train networks to transform continuous XYZ inputs into signed distance or 0, 1 occupancy values. And sometimes they are combined with convolutional image encoders with the MLPs to represent the color and surface details. Mesh SDF can continuously transform SDFs into deformable meshes. All of these networks use latent codes to represent individual instances from a generic class, example a car or a chair, from the ShapeNet dataset. Although they use the codes in a different part of network, allows them to reconstruct the 3D models from just a single image. Pixel aligned implicit function, that is PIF networks, combine fully convolutional image features with neural implicit functions to better preserve the local shape and color details. They are trained specifically on clothed humans and can hallucinate the full 3D models from just a single color image, and it's been shown in a figure. A pixel aligned implicit function, that is a PIFU network, which can recover a high resolution 3D textured model of a clothed human from a single input image. Neural radiance fields, that is NERF, extend this to also use the pixel ray directions as inputs and also output continuous valued opacities and radiance values, enabling ray traced rendering of shining 3D models constructed from multiple input images. This representation is related to lumigraphs and surface light fields. That is, luminance graph means glowing graphs. So, lumigraphs and surface light fields. Both of these systems are examples of neural rendering approaches to generate photorealistic novel views. To deal with the larger scenes, that is buildings with larger buildings and convolutional occupancy networks, first retrieve the local features from a 2D, multiplane or 3D grid, and then use a trained MLP to decode these into a local occupancy volumes. Instead of modeling a complete 3D scene, local implicit grid representations model small local subvolumes, allowing them to be used as a kind of prior for other shape reconstruction methods. Model-based reconstruction. Architecture is usually made up of large planar regions and other parametric forms such as surfaces of revolution, usually oriented perpendicular to gravity and to each other. Heads and faces can be represented using low-dimensional, non-rigid shape models because the variability in shape and appearance of human faces, while extremely large, is still bounded. Human bodies or parts such as hands form highly articulated structures which can be represented using kinematic chains of piecewise rigid skeletal elements linked by joints. In this section, we highlight of the main ideas, representations and modeling algorithms used for these three cases. So first, these three cases, first one is about the architecture, next is about heads and faces, and the third one is about the human bodies or parts. So first about the architecture. The architectural modeling, especially from aerial photography, has been an issue in both photogrammetry and computer vision. Development of reliable image-based modeling techniques as well as the prevalence of digital cameras and 3D computer games has led to widespread deployment of such systems. The earliest hybrid geometry and image-based modeling and rendering systems, which are called as facade system, combines an interactive image-guided geometric modeling tool with model-based stereo matching and view-dependent texture mapping. During the interactive photogrammetric modeling phase, the user selects block elements and aligns their edges with the visible edges in the input images. The system then automatically computes the dimensions and locations of the blocks along with the camera positions using constrained optimization. So the picture, it shows how the architectural modeling is done. So interactive architectural modeling using the facet system. So this is the input image with user drawn edges which are shown in green in color, and this is the shaded 3D solid model, and the C is the geometric primitives which are overlaid onto the input images, and the D is the final view dependent on texture mapped 3D model. This approach is intrinsically more reliable than general feature-based structure from motion because it exploits the strong geometry available in the block primitives. It exploits similar information available from vanishing points. In the interactive image-based modeling system, the vanishing point directions are used to guide the user for drawing of polygons which are then automatically fitted to sparse 3D points which are recovered using structure from motion. Once the rough geometry has been estimated, more detailed offset maps can be computed for each planar face using a local plane sweep, and this is called as model based stereo. So a empty model being created, and to the model the additional details and features of that object will be added up with this basic model which have been basically created. So finally, during rendering, the images from different viewpoints are warped and blended together as the camera moves around the scene using a process called Lumigraph rendering, and this is called view dependent texture mapping. So this picture shows the interactive 3D modeling from panoramas. So different wide angle view of a panorama with user drawn vertical and horizontal lines are created, and after that single view reconstruction of the corridor. So from a single point, if you are viewing this corridor how it is, so it is now recreated. So for interior modeling, instead of working with single pictures, it is better to work with panoramas, as you can see larger extent of walls and other structures. The 3D modeling system first constructs the calibrated panoramas from multiple images and then has the user draw vertical and horizontal lines in the image to demarcate the boundaries of planar regions. The lines are initially used to establish an absolute rotation for each panorama and are later used with inferred vertices and planes to optimize the 3D structure. So which can be recovered up to a scale from one or more images and is being displayed in the picture 13.20. In deep networks, T is possible to both automatically infer the lines and their junctions and to build complete 3D wireframe models. 360-degree high dynamic range panoramas can also be used for outdoor modeling because they provide high reliable estimates of relative camera orientations as well as vanishing point directions. The picture shows automated architectural reconstruction using 3D lines and planes. So the images have been created, that is from the structure of, from the images you create the structure from motion, then it have been converted to lines, segments which have been created like 3D line reconstruction, and from the lines the planes have been inserted and which forms the multiple plane detection, and then the additional details of those has been added to full texture 3D model of the image. And this is the end of the third part of the fourth unit in computer vision.